Oh, that button, right. I was going to say I didn't think I'd followed a heretic before, but I actually don't think that's a true statement. So I want to talk about some, we've taken another look at the illumination conditions at the moon's north pole using the latest data sets. So this work has been done as part of our NLSI work. We developed a very precise simulation tool where you can take a topography file, of which there are now very high quality topography files thanks to the new missions, and very precisely predict the lighting. And from an exploration sense, there's some key parameters that we try and derive. The first is the maximum single period of illumination, and this is relevant if you want to do a lander mission that can't survive any periods of darkness and you want to operate for potentially many months, and you want to land somewhere just before midsummer and operate for as long as possible, knowing that your mission will end when you enter shadow. You also want to determine all eclipse periods, particularly around midwinter. And the idea here is if you want a multi-year mission, and some of the things being discussed, they would like stations that last for many years, then perhaps your key driving engineering parameter is what's the longest single period of shadow that you have to survive, because that potentially drives, for example, your battery mass. The ability to map exact shadow locations, particularly using high-resolution topography, is key for planning rover traverses that stay in sunlight as much as possible. We also consider the effect of mast height, both for power and for communications, and also do some detailed communications analyses, both to Earth and from a rover lander. For the study that's ongoing, and I'm going to present some preliminary results today, we used a LOLA 30-meter digital elevation model and used a 1-hour cadence for the simulations. And we did 6 months worth of simulations, essentially going from midsummer to midwinter. And I like this image. This is a Tony Colopri image showing what a real volatile rover mission on the moon would look like. Okay. We test our simulation tool quite carefully, and if we have two images here, one is an LROC WAC image and one is a simulation, and they are intentionally not labeled. For someone sitting there, I can't believe he didn't label them. We've got to go down and look at this at a pixel level. Emerson Spera from ASU did got a very interesting paper on the lighting studies at the poles, and one of the things he did was consider how well simulations do compared to the WAC data and where you can possibly get errors, particularly at light-dark boundaries when you go down to the absolute pixel level. So that's something we want to work with him and follow up on. But we do think it matches well. I know this is redundant, but I like these couple. But one of the highest resolutions we did was actually a 20-meter, and this is where you have a 20-meter, and then the lighting isn't good, but that's a reduced Knack image down to 20 meters, and again, they do match quite well. So I'm going to take my life in my hands and try a movie. If we could try the first movie. Ooh. So this is a movie that Andy McGovern made. This is This is North Pole from done for 1 year. The red is permanently shadowed. And so we do, it's just an example of how we can take our simulations to look at an overview of the lighting, but this isn't going to work, so I'm going to press the second button. Go. Nope. Yes. Okay, so. Knew I shouldn't have done it. There we go. So here we have sort of the first product that we tend to make. This is the overview. This is the amount, the sort of the mean percentage illumination for. The one nice thing now with computing power is it allows us to do very large areas at very high spatial resolution and very high temporal resolution. So this is sort of the overview, and I'm going to zoom in to some key areas. Probably. There we go. So this is an overview area of just later you have Peri Crater here, 78 kilometers in diameter. This is Hermite, and the three main points I'm going to quickly go through. The results are all in here. But what I think the interesting is just this is a very dark place. You look at here. It is I apologize, like hideous light color scheme we've used for a long time, but I like it. So you can see it is mostly blue and purples here. So most places are lit for much less than half the time. So the places we're going to talk about that receive the most illumination are very small and localized. And you also have a lot of permanent shadow in this general area. Many of these patches are relatively small too. which could be a good thing. Okay, so blowing up, this is just because I'm going to put color on here and grayscale is easier to see. So the three places we found that received the most illumination, we have one up here sort of at the junction of, I'm calling it Peri North, and we have one at Peri South, and this very interesting one on the rim of Hermite. And this point here has been found by multiple studies. I talked about the Emerson study. This was his most illuminated point, and also some of the other people who do simulation stuff like Noda and O in Mazreco. This tends to be agreed upon as the place to get the most sunlight. What's interesting is the simulations. Oh, don't do that. Okay, so put that down. So this is zooming in to the rim of Peri. So this is the place that we thought had the most. Other studies have found the same. The simulations tend to find similar numbers, as I'll go on to. Emerson's work with the images has lower numbers when he looks at the single pixel level, but when he does a clever thing where he expands that by a pixel, he tends to get very similar numbers to the simulations, and I think there's something to learn there. And there are other places, not quite as good as this, that exist on the rim of Peri. And I'll come on to the quantitative numbers in a minute. So this is the other spot. This is the just off the rim of Hermite, and I was going to say, well, look, it looks like a pyramid, but that isn't the type of thing you want to say in a scientific talk. Yeah, if pyramids on the moon doesn't get me on NASA watch, nothing will. Okay, so I was having I was sitting at the back this morning, obviously listening attentively, and I just wanted to see if I could find some imagery of this, and there we go. So I put this up here. This is the wonderful Gigapan that's come out of ASU. It's a 2-meter mosaic, and I put this up here because you should all have a look at this now instead of listening to me. And so this is the region. This is Hermite here. So this is that point that I had labeled. I'm just going to try and zoom in. And this is a wonderful product for exploring. You cannot not get excited to use a double negative to look at this product. You can get not excited about using this. Okay, and then we go in, and I've got one more. So this is almost at the 2-meter level. So this is a great product for exploring some of the places that we're locating. So what we do for all our, that looks actually better than I expected. So this is for all the key places that we find. This is a spiral plot where the radius is subsolar latitude and the angle is subsolar longitude. So this allows us to plot 6 months worth of data in one easy-to-read format, where green symbols mean that this pixel was lit and red means that it was dark. So by doing this, we can start to extract those parameters I mentioned at the very beginning that we want to extract. So we do these for all the key places. And that allows us to get these sort of numbers. So we have sort of, there are several places with getting up over 80% illumination mean. I think some of the key parameters here is, this is the longest period of sunlight, which typically sort of begins at midsummer. So you can essentially double these numbers, because we will do a study for the full year, but we just quickly did midsummer to midwinter. So it's very reasonable that places like this are going to be lit for anywhere between 5 and 6 months continuous based around midsummer. And then, again, this other key parameter, for example, taking Peri N, this longest shadow period of about a week meshes with other studies, including the Emerson study had a similar number for the amount of shadow for this region. Okay, so we also do communications for considering lander assets. We look at individual DSN stations and work out the total amount of coverage that we should get. And then, I apologize, this isn't for the North Pole. We didn't quite get that done quite in time, but the principle's the same. So this gives an example of lander-rover communications. And what we do is, and I'm going to get some silly numbers here, but I'll explain why they're not silly. This shows you, if you have a lander at the red dot, where a rover can go and still talk to the lander, given transmitters at different heights. And I'm going to go through quickly, because I was hoping to just press the down arrow and make this like a movie, but it doesn't quite work that way. So yes, okay, so yes, here, agreed, this is silly numbers, but one of the things we want to do is we want to look at if you could put a lander on the rim of Peri, and some of those little permanently shadowed craters on the floor of Peri are very promising, particularly with the radar data from potential volatile deposits. So one of the things we want to study is if you put your lander on the rim of Peri, how much of those permanently shadowed regions can you actually see? So you could send a rover into some of those places and communicate back to Earth via the relay. So yes, 100 meters is tall, but if you were building a real asset on the ground to explore them, you could certainly have several meters. But the main thing to show is just the technique. So, it's possessed. Oh, there we go. So conclusions. The North Pole region does represent, I think, it shouldn't be forgotten. It is often the forgotten pole as potential exploration sites. Several sites offer multiple months of continuous sunlight around midsummer, as well as relatively short shadowed periods. These locations are close to multiple areas of permanent shadow. That one I showed near Hermite on the pyramid, I think, is very interesting, because if those are manageable slopes, you've got lots of small areas of permanent shadow you could explore and then come back into sunlight. I think also you have the potential for lander-rover combination that enables exploration of permanently shadowed regions. Thank you.
We have time for some questions. Wow. Yes.
To put something in the coffin. Not careful.
Not this time.
Hi. So if you're...
Who are you?
Oh, sorry. I'm Jessica Marcus from NASA Ames. So if you're calculating shadows, so you're also calculating the direction of the sun?
Yes.
Okay. I was just interested to know if you were doing that, because if you try to extrapolate, because this is all rover driven, you try to extrapolate for human exploration, sort of the direction of the sun is kind of important in terms of the human's ability to actually see where they're going.
Oh, you mean whether you don't want the sun behind your shoulder as you're going forward type of thing?
Or right in front of you.
Okay. Other questions? Down here, and then Russell at the back. So.
And I'm free.
No.
Hi, Ben Hockman, Stanford University. I was just wondering, when you show these maps of the illumination percentages,
Yep.
In terms of power that a rover could get from an array, do you need to consider the depth of the rover itself? In other words, if you were to have your array extended up at all, could that significantly improve your capability of gathering sunlight?
Yeah, we can do that for key places. Other people have done that too, like Irwin's done that. You can, you don't want to use those exact percentages, if you like, from a planning, because at the very least your array is probably going to be a meter just above the surface. And that, surprisingly, we did a study about this. Josh Cahill did a study on this a few years ago, and it does make a difference. If you can have 1, 2, or 3 meters, engineeringly feasible mast heights for your solar arrays does actually tweak the numbers more than one might expect.
Last one is Russell.
Thanks, Russell Cox, Fletcher Engineering. So yeah, as you're doing that, you're starting to get to a question I've had for a while, is because the other application is basically pan cams, is how far can you actually see and what kind of, if you're just sitting in one place and you're a meter off the terrain, because it's easy to look at those craters and say, oh, you sit here and you can see this 20-kilometer scene in front of you, but on the moon you can't. So that's another kind of variation of how far can you communicate, but also how far could a stationary or even a robot on a mast pan cam actually give you a scene for.
Well, yeah, and if from a rover perspective, yes, it could be how far do you have to get before you have to communicate again to tell it where to go.
Okay, thanks, Ben. Okay, let's move on. Next is